Okay, hello. This video lesson is going to be on standard enthalpies of formation, and this is this notation that we use for standard enthalpies of formation. This is the final method for determining changes in enthalpy for chemical reactions. So we looked at calorimetry, we looked at bond energies, we looked at Hess's law, and now we're looking at standard enthalpies of formation. And to be honest with you, this is the one that shows up more often on the AP test. Calorimetry and standard enthalpies of formation are the most common types of questions that you'll see on the free response section of the AP test. Alright, so standard enthalpies of formation, essentially what this is going to be looking at how much energy, how much enthalpy is needed to form a substance from its elements at what are known as standard conditions, okay, or standard states. So our change in enthalpy is the formation is to form 1 mole of a compound directly from its constituent elements. Constituent just means the elements that make it up. So its constituent elements would be, for like carbon dioxide, would be carbon and oxygen, and in their standard states. Now we need this idea of standard states because we have to standardize our temperatures and our pressures. Because what we're going to have are different states of matter if we change the temperature and if we change the pressure. So if we have a water, are we talking about water as a liquid, or are we talking about water as a gas? So when we change the temperature, we change the states of matter, and if we change the pressure, we can also have an effect on the states of matter. And if you remember, back when we talked about changes or thermochemical equations, that change in enthalpy is dependent on the states of matter, because if you have a gas, then you have more energy in your system, so more enthalpy, so therefore you have less energy that's released. So we standardize everything so that we talk about everything in their same states, okay, meaning that they're in, what is their temp, or what state of matter are they at 1 atm and 25 degrees Celsius, okay, so that's what we're looking at when we talk about standard states, okay. Now, if elements exist in more than one state at standard conditions, we're going to use the more stable state, okay. So, for example, carbon has 2 different solid forms. We can have solid carbon as diamond, and we can have solid carbon as put another solid here, as graphite. So there's 2 different forms of the solid form of carbon. So which one do we use? Do we use the more stable version? And believe it or not, the more stable version is actually graphite. I know you probably thought that it was going to be diamond, but you're wrong. We'll talk more about that when we get into thermodynamics. We'll talk about why that is a more stable state. This isn't too important. The stuff that you're going to see, you're going to have a table that will help you figure out which one is more stable. Okay, it's going to be based on what we're going to look at in the next slide here. So let's take a look. Alright, so this is a reaction written in its formation. So we have this, this would be ethyl alcohol. Okay, so we've got 2 carbons, 5 or 6 hydrogens, and 1 oxygen. So we are going to form this compound from the elements that make it up. What elements make it up? It would be carbon, it would be hydrogen, and it would be oxygen. And these are the states that they exist in. The idea here is that we're looking at creating this compound from the elements that are that compose it. But the elements are going to be set at 0. So it's kind of like the elements are set as the building blocks for all of our compounds, and we're going to establish them as 0. Okay, so any of the most stable form of any element is going to be 0 for its change in enthalpy. All right, because it's already formed. We don't have to form it. We don't need any energy to form something that's already formed. So our elements are kind of like the baseline. So this enthalpy change, this value here, this change in enthalpy with a little f underneath it means that we are forming this from its elements. So a lot of times you're not going to see this reaction, because you could write that if you needed to. We're always going to make this 1 mole. So this over here is always going to be 1 mole for the reaction, because by definition this is the change in enthalpy to create 1 mole of substance from its elements. That's why we have the 1/2 in here. We put the 1/2 in here to make this come out to be 1 mole. Because the table that you're going to be looking at is going to look a lot like this. This is the chart that we have. We have our changes in enthalpy right here. Okay, changes in enthalpy of formation, and these are the other 2 thermodynamic functions we're going to get to a little bit later, which is free energy and entropy. Okay, for the first one though, we're looking at the change in enthalpy of formation, and notice they just put the substance in here. So if I wanted to, I would write that reaction out. That would be barium solid reacting with sulfur solid, and that would be sulfur 8, I believe, and you would put in here oxygen, and it would be a gas, and it would make barium sulfate, and that would be in the solid form. Okay, so that would be the reaction. All I have to do, and then I could go back and balance this if I needed to. I'm not going to do that, but you can balance the equation. When you do, you need to make this 1 mole because this is the energy for making 1 mole of any of these compounds. Now to check if that S8 was, well, I don't have it on this chart. I'd have to look it up and see. So take a look here. Beryllium, 0. Bromine, 0. Notice we got bromine in a gas, liquid, and aqueous form. Well, the form that we're going to use would be, this would be the elemental state. This would be its most stable version, would be the ones that are 0. Cadmium's most stable state would be 0. So if you ever want to know what their stable states are, you look for the ones that have the zeros in them. Those are the most stable. Hydrogen 2, remember the diatomic versus hydrogen by itself. The hydrogen 2, the diatomic version, is more stable. Okay, and then of course we get to the ions, and we'll talk more about that later. But for now, this is what's known as a standard thermodynamic function chart or graph or whatever. I guess it's not really a graph; it doesn't really have dots and stuff on it, but it's just data. So it's just listing the data here. Okay, you're going to use this quite a bit. I'll give you a copy of this in class. This is from your book. It's from your appendices. So I'm going to actually give you that chart, so don't worry about copying or worry about where you get it. So that's where this number comes from. This 277 comes from, if we look up, oh, I think I cut it off, but it would be down here. It would be, you'd look up that number right there. Okay, it would be one more down if I just missed that one last substance. Anyway, you can look it up in your chart when you get it. So that's where this number comes from. So we're going to look up and see, this is the energy that's released when we form this substance. Okay, this one's 0, this is 0, and this is 0. Alright, so what do we do with this? Okay, so what we're going to do is be able to calculate the change in enthalpy for a particular reaction by using our standard enthalpies of formation, and that's why these are so useful. So we're looking at the reaction. Now this is, you got to go back and compare this to bond energies. Okay, we talked about bond energy. We said the reactants are going to be endothermic because we have to break these bonds, right? Because we have to break this apart so that we can then create our product. So therefore we're going to release energy as we form the bonds on the product side. Now keep in mind the definition here. This is the standard enthalpy of formation. So this is going to seem backwards to you at first, right? Because this is energy of formation. So what I'm going to do is, am I forming these? No, I am not forming these. I am actually breaking these down. What I'm going to do is form these on this side. So our energy values that are in this chart, if you think about this chart here, these are the energies of formation. Okay, so if I'm forming this, then the energy is released. If I am breaking it down, then I have to make it positive. It's kind of the opposite of what we did with the bond energy chart. The bond energy chart was almost always positive. A lot of these are all going to be negative. So keep that in mind as you're looking at this. Now, if you use this equation down here at the bottom, what this equation is going to do is by putting products minus reactants, it's going to change the sign notation for you. Because if you're subtracting the reactants, your reactants are the ones that you want to change the sign notation for. Okay, with bond energies, we change the sign notation of the products. Here we're changing the bond energies of the reactants because we're not forming these, we're breaking them apart. Okay, I'll show you an example, so just kind of bear with me here. Okay, so what we're going to do is we're going to sum up this side just like we did for the bond energies. We're going to sum up this side and then we're going to compare the two. But this equation kind of does it for you, and I like this equation, so I would recommend you try using this. What this means is a summation, so you're going to sum up all of your reactants or all of your products. The M stands for the coefficient, so that would be your coefficient, so you have to take into consideration the coefficient that you have. And then this is your change in enthalpy of formation. And the little degree symbol, I don't know if I mentioned that earlier, signifies standard state. Okay, so that's what that means is that we can use this chart because this chart is under standard states as well. Okay, all right. So what we're going to do is sum all of those up, and then we're going to take the summation of the products and subtract it from the summation of the reactants, taking into consideration the coefficients. Okay. Okay, so I'm going to use standard enthalpies of formation to calculate the change in enthalpy for this reaction. I changed this from reaction to combustion just because I know that it's a combustion reaction, and you don't necessarily have to do that, but it just kind of helps to recognize this as a combustion reaction. Alright, so I wrote down the equation. I got the summation of the products and the summation of the reactants. So I'm going to rewrite this in terms of the substances. Okay, so what I did was I replaced the reaction. I've got the M is my coefficient. So I put that down here for each of these. And then I just replaced products with the actual products themselves. So now I'm going to do is I'm going to use my chart over here and I'm going to plug in the numbers. Okay, so I'm going to plug the numbers into the equation. Alright, so let's do that. Okay, so I replaced this information here. Let me do a different color. I replaced this information here from the chart. Okay, I replaced this over here. Now notice that this one here I put as a 0 because anything in its elemental state, like oxygen or hydrogen, is going to have a value of 0 if you look it up on the chart. Now, one thing to watch are the sign notations: negative, negative, negative. You don't have to remember to change them like we did with the bond energies. Just take them from the chart as they are, plug them into the equation, and you should have no problems because this is going to self-correct the sign notation. Okay, it's going to self-correct it for you. I'm going to finish simplifying all of this, and we'll take a look at the answer. I simplified everything and brought all my units together and finally got my answer, which is negative 1,357 kilojoules. That would be the change in enthalpy for the combustion of this reaction. So for every 1 mole of the ethanol that reacts, this is the amount of thermal energy that comes out of the combustion reaction, and that's the number that goes here. All right, a couple things to look at is keep in mind if they might give you this number. One typical thing that they do is they'll say that the heat of combustion is, because you can get this from calorimetry. Remember, we can put this in a calorimeter and experimentally find that heat of combustion. Then they might say, well, what is the change, or what is the formation energy of the ethanol? Well, you can look up this number and this number, and you would be solving for this. It's a very, very typical problem that you could see in the AP test where they don't actually have you solve for the combustions because we can actually get those from experiment. The formation energies are sometimes hard to determine if it's a new substance. So, all right, so that's really important to focus on because we're going to use this for all types of state functions. So we're in free energy and entropy. This strategy is used quite often. So I hope that helps you get started, and I will see you guys in class.